So we learn a lot from Manju at Momento, and he's here to tell you about designing a flexible search system in the age of embeddings.
Thank you, Khwaja. I put these slides together yesterday, and I forgot to even put a slide on about me. I'm a VP of engineering at Etsy. This year, I'm running 2 groups there. One is machine learning enablement, which this group is responsible for democratizing machine learning across the product portfolio at Etsy, and our other group is driving personalization experiences. I've been at Etsy for more than 6 years, and over that tenure, I've run the search group, the ads group, the recommendation group, the core buyer experience group. I came in to Etsy to an acquisition of a company that I was a co-founder of. We did multimodal deep learning, combining text, images, and user feedback. We started out in 2013, and a lot of our customers were e-commerce customers because a lot of search and recommendations there is very, very visually based, and that ended up being our initial set of customer base. Prior to Blackbird, where I was a co-founder, I was very early at Twitter, where we built a lot of caching systems. So if you've ever used Twem Proxy or Twem Cache, those were some of the pieces that we open sourced around that time. And so that's a little bit about me, and a lot of the things that we're sharing today is based on some of the learnings that we have had as we built scalable search systems and also incorporate machine learning with them. So the talk today is designing a flexible search system in the age of embeddings. So a lot of buzzwords here. So let's unpack that a little bit. And so the goal today is I really want us to walk through an incremental approach for building a search system with the focus on extracting repeatable value, repeatable incremental value, and maximizing design flexibility. So if you look at the search that is being built today, and you compare that to a decade ago, machine learning is now becoming a really integral part of search. Right now, we moved beyond information retrieval. If you look at large language models, it's really changing how search systems are built. We're seeing that with how Bing and Google are bringing large language models into the search experience. So it's really having flexible search system is a good goal to have, so that we don't pigeonhole ourselves into a design space where we can't really iterate our search system because the design is not flexible. So that's one of the goals. The other goal is search seems easy, but it's actually really, really hard. And getting it right is even harder. So it would be nice that we don't spend a lot of time before we can reap the benefits out of search. So the other goal of this talk is how can we extract repeatable incremental value along the way as we build it. The talk is also a system design talk, so I've organized it as a collection of insights, and they kind of take the first principle approach. We'll start from the very beginning and build upon each other. And my hope is that by the time we get to the end of the talk, all of you would have a good mental model for how to build search systems, maybe in your own organization for your own project, and also in a way that it's flexible and you can kind of extract repeatable value out of it. So let's get started. The first insight is actually search is an exercise in retrieval and ranking of items that are relevant to the query. So there are 3 operative words that are called out here. The first is retrieval, the second is ranking, and the third is relevance. And so let's understand what we mean just through an example. So here's an example of search on the Etsy marketplace. On the Etsy marketplace today, we have more than 100 million active inventory. And so when you search for teardrop earrings, you get close to 45,000 results, right? And so that actually is the retrieval, right? So the retrieval is out of the entire 100 million inventory, we're finding 45,000 items or products here that are relevant to the query. Now, out of those 45,000 items, the search decided to show these items, the 8 items here shown in the screenshot on the first page of the search result. So that is actually ranking, which is it's deciding to, of all of the relevant items, it decided that these 8 items are the most relevant, so it needs to be shown on the first page. So retrieval is the exercise in finding all of the relevant items to a query, and ranking is the exercise in sorting the items based on the degree of relevance. right? And I still haven't defined what relevance is, but let's put a pin on that because there's a little bit more to talk about there. So if you take the retrieval and the ranking approach of viewing the search system, then the search becomes a two-stage process. The stage one is that where we send a query and we find and match all the items that are relevant to the query. And stage two, which is the ranking, where we rank the results based on the degree of relevance. And you get those results and you send it back to the user. And since this is a system design talk, the immediate question that follows up from here is that what are the building blocks of the ranking and retrieval layer in this search stack? So let's take a look at the first building block. We've heard the word index a lot today. We introduced the vector index. Khwaja introduced it today in the morning. And index is kind of the powerhouse for driving retrieval in search. And the most canonical way of doing index, this is something that we're all kind of familiar with, is that if you've ever picked up a book and you've gone to the back of the book, you find an appendix, and the appendix lists out all the words in the book and which pages they appear on. So in this screenshot, we have words like bush tip that appears on page 36 and page 57. We have the word called dog's life that appears on page 12 and page 57. So I'm looking for a page that contains the word bush tips and dog's life, go to page 57, right? And so that's an example of an index. It allows you to get to the information really, really quickly. And it has some sort of a data structure associated with it. When you kind of pull that analogy to search, we have an index too. And in search, especially for text retrieval, we have an index that we call as the inverted index. And in this example here is we decided to index all of the pages in the Shakespeare book. And if you're looking for the word Brutus and Caesar, you get all of the documents where all of the pages where those words appear. They are like the sorted merge list. We call them posting list. You merge them and you emit the common entries, and that's retrieval. Now, inverted index has been there for a long, long time. It's been there for like decades and decades. They are fast. They answer certain sets of queries really well. They're horizontally scalable, and they're not going to go away. So as a building block, it's a really great building block for solving the retrieval problem. So with retrieval solved by the inverted index building block, the next question is what's the building block for ranking? And we said that ranking is a measure of degree of relevance, whether this result is more relevant than the other result. And the best way to kind of define that is by a function. So the building block for ranking is a ranking function. And one way to build a ranking function is to just hand build it, right? So if you're trying to find a query, like teardrop earrings that we saw before, and match it to a document, you can figure out a text similarity score like TF-IDF or BM25 or anything that you come up with. You marry that with a business objective, and you put that in a function that you kind of create from thin air, and now that's your ranking function, right? So let's say in an e-commerce marketplace, you say, I want all products that are teardrop earrings, but my business objective is I really want the ones that are on sale to show up more, right? And you kind of marry them together, and that becomes your building block. So at this stage in our design exploration, we've kind of identified two building blocks in this two-stage view of a search system. The retrieval building block is the inverted index. The ranking building block is this hand-tuned ranking function, right? And this is enough. If you build this and you deploy this is enough to get you the first incremental value out of search. You don't need anything else, right? But this is setting the baseline. The next step, which I'll take us to the next insight, is what shows up on page one matters the most. The other way to say is that what shows up on any other page is just gravy because nobody cares. And the best way to have this insight is that going back to the example where you search for teardrop earrings, your 45,000 results, how often, just with folks raising their hands, how often do you think a user would have paginated all the way to the last result? 0? Yeah? How often do you think people would have paginated beyond page 10? Never? 0.1%, 0.001%? Okay, 0.001%. How often, if you were a buyer on the Etsy marketplace, you would paginate beyond page 1? Maybe 5, 10%, right? But you want the result to appear on page 1, right? And so like search, so ranking in search is super important. It's not like a database, right? You select start from table, you want to see all your results are really correct, and you'll eyeball them, you'll like verify them. With search, it's like, I really want all of the results on page 1, page 2, maybe page 3 to be correct, but you don't know what's happening on page 20th or page 30th, right? So getting ranking right is vital in search, and that is your entire performance, entire perception of a search system is depending on what's happening on page 1. But there's one caveat. There's a lot of implicit and explicit intent that needs to be inferred from a search query. The explicit intent here is clear. The buyer is searching for teardrop earrings, but the implicit intent is not. Is the buyer wanting to buy a gift for themselves right now, or are the buyer more interested in the window shopping behavior? Is the buyer, does the buyer have a preference? Do they prefer more gold teardrop earrings, or do they prefer a more minimalist style? None of that is there, and that's where the implicit intent is there. And the big piece of the implicit intent is that it's never knowable. So in the whole building blocks approach, we were trying to come up with a ranking function, but the assertion is that the ranking function will always be trailing the ideal ranking function, and the ideal ranking function is unknowable. So even if and the only person who knows it would be an oracle who knows all of the information to figure out the ideal ranking function, right? But most of the exercise in building a search system is to kind of build this ranking function that can best proxy the ideal ranking function. And we know a mechanism for doing this, right? We've been living through it, which is machine learning and AI, where let's use the data from buyers and use machine learning to build this ranking function, which is what we'll do next, right? So we took our search system, which had the retrieval layer, which was an inverted index, which had the hand-tuned ranking function. We deployed in production. We then look at user behavior. Now, given the search result, did the user interact more with the first search result or the second search result, or did the user just bounce? And that becomes your training data. Now you can start training your machine learning model, and that becomes your ranking model. So the next step in evolution of this design exploration is that we grow from a hand-tuned ranking function to a machine learned ranking function, right? So great, and so we have retrieval, that's the inverted index. We have the ranking layer, which is the machine learned ranking function, and here is our two-stage view of the search system. So the next insight is actually investing early in a real-time ranking system. What I mean by that is that you want all of the queries that your search system gets to be ranked in real time. So your ranking function is operating in real time. And that actually opens up, with machine learned ranking, that opens up a space, and we call that as a design space. The design space here is that you could either apply the ranking in real time, or you can apply the ranking in an offline setting, right, or in a batch setting. So in the real-time setting, it's a little bit harder, right, because you want your models to be performant. No one wants to be typing a query in the search box and then wait for 2 minutes for the results to show up, right? So that's not going to work, right? And so that's the real-time ranking. And the other side, when you do an offline ranking, you do all of your ranking in an offline setting, but you either don't have access to the queries, or you only do it for a limited set of queries, right? So if you look at these like pros and cons, it feels like static ranking is like an easier approach, right? And for anyone building systems, you kind of like build the easiest thing first, and you kind of build and start making it harder over time, and you don't go about building the harder thing first. And the insight here is the opposite. It's saying that let's go about building the real-time ranking system first, and the reason for that actually comes from data. and this is like a data-driven approach to designing systems, where we're looking at the data, and here's a typical, this is not to scale, but here's a typical distribution of queries in any given search system. And so what you have on the x-axis is all of the queries that the system has seen over a period of time, like let's say 12 months or something like that. And on the y-axis is the frequency which it occurs. And you build a histogram out of it. And we've segmented it into multiple segments. So you have the head, which are the queries that often occur really, really frequently. So in the Etsy marketplace, that could be a query like couch or query like earrings. Those are like head queries that are appearing very, very frequently. And then as you go further and further down this, the reverse power law graph, you'll get these like really tail queries, like red cocktail lace dress. That's a tail query, but they don't occur very, very frequently. But the insight here is that if you take the area below the tail distribution and the deep tail distribution, it far exceeds by volume the head queries. So if you go back to the earlier thing where we say, let's build a ranking system, but do it in an offline setting, use the batch infrastructure to run your ranking model against all your queries, that value the new net value of that ranking function is only applicable to a certain segment of queries, like the head query distribution. And you can't do it for all of the queries. So you do all of the work to build this like really performant ranking model, but only a subset of your query distribution get the value. So it's like not super useful, right? And so this is why it's like good to just go to take the hit and build a real-time or dynamic ranking system. And as soon as you make that decision to build a dynamic ranking system, it actually opens up the design space. And this is the most interesting piece around bringing machine learning to search. The design space actually has 3 different knobs. The first knob is the model complexity. It's like, how complex are your models? Like, do you have linear models? Do you have tree models? Do you have neural models? Do you have like really, really big neural models with like billions of parameters? Like, that's the model complexity. And we know that the more complex a model is, the more performant it is, at least to a certain degree, right? So that's the first knob. But model complexity also adds cost. Linear models are really cheap, really quick, right? And large language models are really expensive. So that's a trade-off. The second knob is the feature space. Like, how many features does your model need in order to do its task? Like, does it need 100? Does it need 1,000? Does it need 10,000? Does it need 1,000,000? And does it need 1,000,000,000? So that's the feature space. And what are the sizes of those features? So that's the second knob. And the third knob is, how many candidates is the ranking function ranking? So the ranking function is the sole task of the ranking function is to figure out the degree of relevance so that it can order the results on the search page. And there is a bound to it. It can rank 100 items, it can rank 1,000 items, it can rank maybe 10,000 items. But as you start going beyond that, you have to rethink the whole system design around how are we going to do it, right? So that's the design space. But so given this design space where we have like these 3 different knobs, we still want to go back to the earlier point, is like, how can we create repeatable value with this design space? And what we found is it's better to start with something simple and have something end-to-end working. So in this case, you start with a linear model, make it work with re-ranking of like 100 to 1,000 candidates, and use a feature space that is smaller, like 100 or 1,000 features. And once you have that working, then you can have 2 kinds of tracks of work that comes out of it. One is you can focus all of your efforts on model-centric improvements, and the other is that you focus all of your efforts on system-centric improvements. And the model-centric improvements is like making the models more and more complex. And as you make them more complex, you'll realize that your latency starts increasing and your feature space starts increasing. And in order to combat that, you start bringing more system improvements and optimization. Putting caching at the right time. If you need 1,000 features, but only 500 of them are really important to the accuracy of model, you just fetch those 500. So you can start doing these optimizations where you can start making your models more and more complex, but still make it run in a real-time setting. And now you have a real-time re-ranking system that you can have it productionized, and you have a repeatable playbook for extracting value out of this entire system. And so bringing back to where we are in this design exploration, we have the ranking, which is machine learned function. We have ranking, which is real time, which by very nature also introduces some constraints. The constraints are, if you look at ranking and retrieval, the inverted index retrieval can operate over a big cardinality, right? And so here is represented as O of n, and so it could operate over like 100 million items or 1 billion items or even more, and that's retrieval, right? But when you come to the ranking layer, it's operating at a cardinality which is a lot smaller, right? And what we found is like anything between 1,000 items to 10,000 items, depending on the complexity of the ranking model, you can make it operate. But it kind of gives you a design space of like what to choose and when to choose, right? And so you can continue working on this design space to keep getting value out of ranking, but at some point you reach a plateau, right? Because ranking is only as good as the candidates that the retrieval sends to it. If the retrieval layer is doing a really bad job at sending it the right candidates, no matter how good the ranking function is, it's not going to do a job, right? So this takes us to the final insight, which is investing in multiple retrieval engines to maximize flexibility, which also brings us why embeddings are really important. So let's go back to the current building block for retrieval, it's inverted index, right? And let's look at teardrop earrings. Now, the inverted indexes are really great. They're super fast. But one of the things but you have to do a lot of workarounds in order to do semantic search with inverted index. And what we mean by semantics is really understanding what the user meant when they said, oh, I really want teardrop earrings. And there are multitudes of ways in which it could break. The first is, like, if you don't have the right synonyms, that's going to break. Now, if the user typed in teardrop earrings, you also want to return earrings that are tear-shaped or pear-shaped. Now, it seems like logical. So if you're using an inverted index, you have to work around that in order to make it work. You also have a hypernym and hyponym mismatch, right? If I typed in teardrop earrings, I also want teardrop studs to show up because studs is a subcategory of earrings. So there's a semantic grab problem with inverted index, and there are multiple ways in which it can break. But there's also limited modality. The inverted index is really great for text retrieval. But our retrieval is moving beyond it. Like we want to retrieve based on images. Like, how does image search work? If you want to make image search work using an inverted index, we have to take that image, convert it into words, and then search our inverted index. And that seems backwards. Like, can I just use the original representation of my input, which is that great image? All right. And similarly, how about like searching for a multimodality where you have input as words, but you might also want an image associated with it, right? I want a painting, but I want a painting in this style, and the style is an image input to the search system. So multimodality is becoming more and more common, and we're seeing that with like large language models where the input is text, the input is code, the input is images, the input is like video screenshots, or the input is a combination of that. So the shortcomings of inverted index implies that we have to change our input representation. Right, and the input representation here is the concept of embeddings. We can do that with the Momento index today if you wanted to, right? There's a nice API for inserting and retrieving vectors, but embeddings are really a collection of vectors. And in this example, you have a query, you can map it, you can pass it to an encoder that you learn as part of your learning process. It embeds, it spits out an embedding. You do the same thing with the document, and if they map into the same space, then they are similar, which means they're relevant. So to the screenshot on the right, here it's a three-dimensional embedding because everything is embedded in the three-dimensional space. And if your query and your document map to the green space, then they're similar. If not, they're not. So that's kind of the idea behind the embeddings. But if you have the embeddings, we can bring that embeddings to to the retrieval layer. So let's explore how we can do that. And this is just a first principles approach of like exploring how can we make an embedding work, right? And so instead of like an inverted index, let's throw it out, and we say for every query that the search system has ever received, let's use the embedding mechanism to generate the embeddings for it. And for every query, let's do the ANN search, pre-compute the results, and store it. Now that becomes your static index. That works, but it has a couple of shortcomings. We can't pre-compute it for every query for the same reason that we talked about. The query distribution is really, really large, so it's computationally impossible. The second is, how do you deal with staleness? You're doing this pre-computation in a batch system. Your products might get deleted in the day, but your information was pre-computed a day ago, right? So there's the staleness issue, which is hard to capture. And there are these like first-class constructs that you kind of expect out of a search system. Like you want to filter it. I want teardrop earrings, but I want them all under $100. Like how do I do that filtering under $100? And you also want facets. And none of that is clear of how you're able to do it. Maybe if you can solve the facets, you'll still have the staleness problem with it. So you might say, you know what? Okay, I see the problems that you're talking to me about. How about we do both, right? So instead of you have a static index, I'll keep the static index there, but I'll also put my inverted index right there. Now, if a query comes in, I will route it to the right index, which might immediately lead to the question, like, how do I know which index to route? We go back to the principles of machine learning. We deploy the system, and we see that which index is returning the right results, and we can learn a routing model out of it and put the routing model there, right? So that's one way to solve it. And let's see whether can we pre-compute it for every query? Yes, because we have an inverted index. So what doesn't work in the static index can now work in the inverted index. How do we deal with staleness? Still not clear, because the items is coming out of the static index is still stale, and we still don't have faceting and filtering from the static index. So you may say, okay, how about let's take this static index and let's bring in a vector index. And the vector index is more real time, where you get a query and the retrieval process does an ANN search, and you get out of the vector index. But it still has the same problem that everything works, but we still can't figure out how to address staleness, because the vector indexes are being built. We still don't know how to do faceting and filtering. But we have like multiple retrieval engines, and each of these retrieval engines are kind of becoming experts in their own domain. The text retrieval is really good for point queries. If you type in CNN, inverted index would be really good at giving you the Wikipedia page of CNN or CNN.com, right? But if you type in a query that is more semantic, right, you want a neural index to do it, so that it can go. So what's happening is that the retrieval layer is moving into the systems of experts model, where every retrieval engine is an expert in its own domain, right? And the way to make this work is if you can put in a blending layer on top of these multiple retrieval engines, and if you have the same result coming from two or more retrieval engines, you can promote it higher up and send it to the ranking layer, right? But it still doesn't solve the faceting and filtering problem, and we still haven't talked about it. We know that inverted indexes solve filtering really well, but we don't know how to do filtering on these newer retrieval engines like neural index and static index. And the idea there is you bring in out of band filtering solution, where either you roll out your own ANN solution where the filtering is part of it, or you overfetch from the retrieval engines, and then you do an out-of-band filtering. But the end result for the ranking layer is just getting a bunch of great candidates out of these like systems of experts for retrieval. And you have this like nice two-stage ranking system with two-stage search system with ranking, multiple retrieval engines, and things like filters that are now just first class in this new world. So the overall takeaway for anyone wanting to have a really good mental model for search systems is to start viewing it as a two-stage ranking system, as a two-stage process, where the first stage is retrieval and the second stage is ranking. And both of them can evolve separately, and both of them could be, and that evolution would allow you to make changes to them independently. The second is to invest early in building a real-time ranking system and not shy away from it, even though that upfront investment may seem a lot. But because once you have a real-time ranking system, you have a repeatable playbook for extracting value, because you could just focus on improving your models, and your ranking performance continues to increase. You can focus on improving a system. We can bring in system optimization that would allow the newer improvements of ranking models to work in real time. And the final takeaway is, when thinking about leveraging retrieval, think about leveraging multiple retrieval engines. So you can bring in the vectored index, you can bring in inverted index, and you can make them all work together. But the key there is to figure out how can you make these first-class constructs work really well, which is how do you make filters work really well? How do you make facets work really well when you have multiple retrieval engines? Well, that's all for today.